In this lecture, we prove a property of the monic Chebyshev polynomials that are defined on the interval from -1 to 1. That property states that on the interval from -1 to 1, the monic Chebyshev polynomial has the least maximum absolute value out of all the monic polynomials of the same degree. A formulation of the monic Chebyshev polynomials t sub n of x, whose degree is n greater than or equal to 1, for the interval from -1 to 1 has t sub n of x equal to the product from k equals 1 to n of the linear factors x minus x sub k, where x sub k equals cosine of 2k minus 1 times pi divided by 2n, and k goes from 1 to n. The exception is t sub 0 of x, which is equal to 1. We denote the maximum absolute value of a polynomial p of x on the interval from -1 to 1 by max absolute value p of x. The main result in this lecture is the following theorem. Max absolute value q of x is greater than or equal to max absolute value t sub n of x for all monic polynomials q of x with degree n greater than or equal to 0. To prove this result, we first examine a derivation of the formula for the t sub n's. Then we prove a couple of mini theorems or lemmas that we will use for the proof of the theorem. A derivation of the formula for the t sub n's uses the substitution theta equals arc cosine x for every x on the interval from -1 to 1. As such, cosine theta equals x, and theta is on the interval from 0 to pi. For every non-negative integer n, let p sub n of x be equal to cosine n times arc cosine x, so that p sub n of x equals cosine n theta. And so, for n greater than or equal to 1, p sub n plus 1 of x equals cosine n plus 1 theta, which is equal to cosine n theta plus theta, which is equal to cosine n theta cosine theta minus sine n theta sine theta. Similarly, p sub n minus 1 of x is equal to cosine n theta minus theta, which is equal to cosine n theta cosine theta plus sine n theta sine theta. And so p sub n plus 1 of x plus p sub n minus 1 of x equals 2 cosine n theta cosine theta. With cosine n theta equal to p sub n of x and cosine theta equal to x, we get the following recursion. Here is the first of our two lemmas. For n greater than or equal to 1, the lead coefficient of p sub n of x is 2 raised to the n minus 1th power. We prove this using mathematical induction. When n equals 1, p sub 1 of x equals x, which is equal to 2 raised to the 1 minus 1th power times x, and so the lemma is true for n equals 1. We now suppose that the lemma is true that the lead coefficient of p sub n of x is 2 raised to the n minus 1th power for n equal to 1 to k for some k greater than or equal to 1. To complete the induction proof, we show that the lead coefficient of p sub k plus 1 of x is 2 with exponent k plus 1 minus 1, or 2 raised to the kth power. We apply the recursion. P sub k plus 1 of x equals 2x times p sub k of x minus p sub k minus 1 of x. By our supposition, p sub k of x is 2 raised to the k minus 1th power times x to the kth power, plus terms of degree less than or equal to k minus 1. P sub k minus 1 of x only has terms of degree less than or equal to k minus 1. After multiplying p sub k of x by 2x, the lead term of this polynomial simplifies to 2 raised to the kth power times x to the k plus 1th power. And the terms of lower order with or without the multiplication by 2x will produce terms all of whose degrees are less than or equal to k. Therefore, the lead coefficient of p sub k plus 1 of x is 2 raised to the kth power, and this completes the induction proof. For the second lemma, we proved that for n greater than or equal to 1, max absolute value of t sub n of x is equal to 2 raised to the 1 minus nth power. We will eventually define t sub n of x to be the monic polynomial version of p sub n of x, which is not necessarily monic. P sub 0 of x is equal to 1, and so is already monic, so that we define t sub 0 of x to be equal to p sub 0 of x. For n greater than or equal to 1, the lead coefficient of p sub n of x is 2 raised to the n minus 1th power, and so we let t sub n of x be equal to 2 raised to the 1 minus nth power times p sub n of x. T sub n of x is now monic for all n greater than or equal to 0. And so to begin the proof of lemma 2, we have for n greater than or equal to 1, max absolute value t sub n of x equals max absolute value of 2 raised to the 1 minus nth power times p sub n of x. Now, this is equal to max 2 raised to the 1 minus nth power cosine n theta, since p sub n of x equals cosine n theta. Now, we can take out 2 raised to the 1 minus nth power, so that this last quantity equals 2 raised to the 1 minus nth power times max absolute value cosine n theta. And max absolute value cosine theta equals 1. Therefore, max absolute value of t sub n of x equals 2 raised to the 1 minus nth power. And now we prove the main theorem of this lecture. N equals 0 is the trivial case, because the only monic polynomial q of x of degree 0 is 1, to which t sub 0 of x is also equal. For n greater than or equal to 1, we use proof by contradiction. And so we assume that max absolute value q of x is less than max absolute value of t sub n of x. Since max absolute value of t sub n of x is equal to 2 raised to the 1 minus nth power, q of x lies strictly between the negative of 2 raised to the 1 minus nth power and 2 raised to the 1 minus nth power. Since t sub n of x equals 2 raised to the 1 minus nth power times p sub n of x, which is also equal to 2 raised to the 1 minus nth power cosine n theta, we check the graph of 2 raised to the 1 minus nth power cosine theta. On screen is the graph of one cycle or one period of the graph of cosine theta. We can copy the cycle or period and simply paste it all throughout the real line to get the graph of cosine theta for the entire real line. For cosine n theta, with n equal to the frequency, we get n cycles or periods on the interval from 0 to 2 pi. For example, we get 2 cycles or periods when n equals 2, and when n equals 6, we get 6 cycles or periods. Now, we are restricting 2 raised to the 1 minus nth power cosine theta to the interval from 0 to pi. And on the interval from 0 to pi, we only get half of a cycle of 2 raised to the 1 minus nth power cosine theta. And on this interval from 0 to pi, we get n half cycles or half periods of t sub n of x, or 2 raised to the 1 minus nth power cosine n theta. On screen is the graph of t sub n of x, where n is equal to 2, and so we have a full cycle on the interval from 0 to pi. On each half cycle, the graph either goes monotonically from its highest point, where y is 2 raised to the 1 minus nth power, to its lowest point, where y equals the negative of 2 raised to the 1 minus nth power, or it goes monotonically from an absolute minimum to an absolute maximum. Now let us take the graph of q of x. Actually, it's the graph of q of cosine theta. By assumption, the graph of q of x lies strictly between y equals 2 raised to the 1 minus nth power and the negative of 2 raised to the 1 minus nth power. Let us follow the first half cycle of t sub n of x, which is really t sub n of cosine theta. T sub n cosine theta starts at its maximum point, where q of cosine theta minus t sub n cosine theta is less than 0. T sub n finishes at its lowest point, where q of cosine theta minus t sub n cosine theta is greater than 0. And so, invoking the intermediate value theorem, q of cosine theta minus t sub n cosine theta equals 0 must have at least one solution in theta on this half cycle. This is also true for the rest of the n half cycles of t sub n, so that q of cosine theta minus t sub n cosine theta equals 0 must have at least n distinct theta solutions on the interval from 0 to pi. Since the cosine function is a one-to-one function on the interval from 0 to pi, and cosine theta equals x, these n distinct theta solutions correspond to n distinct solutions in x on the interval from -1 to 1 for the equation q of x minus t sub n of x equals 0. With at least n distinct zeros, the polynomial q of x minus t sub n of x must have degree at least as big as n. Now q of x and t sub n of x are both monic, and both have degree equal to n, so both are equal to x to the nth power, plus their own respective lower order terms. X to the nth power cancels out when we subtract t sub n of x from q of x, so that the degree of q of x minus t sub n of x is less than n. But this contradicts what we have found earlier, that the degree of q of x minus t sub n of x is greater than or equal to n. And so our assumption that max absolute value of q of x is less than max absolute value of t sub n of x is false. And therefore, max absolute value q of x is greater than or equal to max absolute value of t sub n of x. And that of all the monic polynomials of degree n, t sub n of x has the least maximum absolute value on the interval from -1 to 1.